Okay, I'll get started. Wanted to begin with the exam one, test one announcement. Just a reminder that it's next Thursday, so 1 week from now. It will be on Zoom. You'll connect to the regular Zoom lecture. It will be open book and open notes, but no internet or Google resources. It will contain multiple choice. There'll be 6 multiple choice questions worth 4 points each. It'll contain numerical answer questions. There'll be 9 numerical answer questions worth 5 points each. And then there'll be one fully worked out problem. You'll upload a PDF, a JPEG, that's 31 points. That all adds up to, cleverly, 100 points. It will cover all the material since the very beginning of the semester through next Tuesday's class. So it's going to cover discussions of electric charge, discussions of electric forces, discussions of electric fields, discussions of electric flux, and discussions of electric potential, the theoretical basis of electricity. And then it will cover our work on capacitors, our work on resistors, and the work we'll do in today's class and the next class on electrical circuits. Any questions on all that? I'm watching chat.
Will the quiz be a Canvas quiz or will you be like giving us a document?
Yes, so let me be clear on that. It's a good point. The test will be a Canvas quiz. And so I will publish that Canvas quiz, at 12:30 on Thursday, next Thursday.
Is there any partial credit for like the numerical questions, or like do we not show our work? So it's just like if you miss one, you just miss all 6 points?
Yes, so that is true. The partial credit is on those 31 points that are the fully worked out problem, where you actually submit your solution to the problem. The numerical answer questions, there is no partial credit. So they're 5 points each. So you either get that 5 points or you don't get that 5 points. I sort of wish it wasn't like that, but the practical matter, I think it is going to be like that. I tried to keep that number of points relatively small.
Okay, thank you.
Any other questions on the upcoming test or getting ready for it? Would we have to download or print out something prior to the exam? No, you don't have to download or print out something. You have to write out your solution to the long problem, the fully worked out problem, and then you can scan it or take a photo of it and upload it. So you don't download or print, but you do upload a solution. Can we go back to previous questions? Yes, you can go back to previous questions. Okay, well, if you have other questions, you can always email me. You can always ask them at the end of the class. I'll stay on the end of the class for a while. Or I've got office hours today and I've got office hours on Monday. So today's class, and actually Tuesday's class, we're going to move on to solving problems involving electrical circuits. And I just wanted to sort of give you an overview of, solving problems with electrical circuits first. So here's an example circuit that I've sketched out here. And if you look at this circuit, maybe it looks mind-blowingly complicated. right? It contains resistors and batteries, but it's not a simple, you know, parallel array of resistors or series array of resistors. It's a complicated circuit. And in general, electrical circuits are complicated arrays of components with maybe one or more sources of power, batteries, and components like resistors that are both in parallel and in series. And so our job is to learn how to solve the currents through the different components in the circuits, how to find the potentials across the different components in the circuits, and so on. That's going to be one of our tasks. So I'm just showing you that picture with this in mind, that our circuit problems will generally involve figuring out the currents and the potential differences across various circuit elements. Our problems will also involve figuring out the power dissipated in, or the energy delivered to, or the power supplied by, the energy supplied by the different components in the circuit. So this will be another topic of our circuit problems. So the way I think about, I mean, I don't know whether this is going to make you feel better or going to make you feel worse, to be honest. The way I think about electrical circuit problems is they're kind of like Sudoku problems. You know, Sudoku problems, the rules are kind of simple. But, you know, solving, you know, Sudoku problems are not always simple, and it needs some experience and some practice. Circuit problems, also circuits involve some simple rules, Ohm's law. But, you know, circuit problems are not always simple problems. They're sometimes much more complicated problems. And again, solving them needs some practice, needs some experience. So in that sense, Sudoku problems are like circuit problems, or vice versa. Now, if you like Sudoku, maybe you're feeling pretty good right now. If you hate Sudoku, maybe I've just made your day worse. So specifically today, I want to cover one topic is electromotive forces and batteries. So we're going to explain electromotive forces and batteries. I'm going to talk about arrangements where you have resistors in series. And I'm going to talk about arrangements where you have resistors in parallel. And then we're going to put those rules together for resistors in series, resistors in parallel, and see how we might solve circuits involving both series and parallel combinations. That's something we hopefully will get to start today, but it's definitely something that will continue in the next class. Okay, so a few words about electromotive force, what's that? And a few words about batteries, a little more of what's that too. So specifically, I want to talk about the concept of ideal and real batteries and the electromotive force provided by batteries. On this slide, I've pictured two circuits. So let's talk about this one over here on the left. I've got a battery in this circuit, and it's providing a potential difference between the terminals of the battery, the positive and the negative terminals of the battery. A resistor downstairs here is connected to the battery, to the terminals of the battery, and electrical current flows from the positive terminal of the battery through the resistor around to the negative terminal of the battery. And so we've built a circuit. And so this is a very simple circuit involving just a battery and a resistor. And we see the idea of the potential difference supplied by the battery, the current that's driven by the battery. On the right, I've drawn an expanded view of the circuit, in particular, an expanded view of the battery. So this dashed box here is the expanded, more detailed view of the battery and the potential difference the battery has provided. Now, this expanded picture, more detailed picture, is for the following reason. An ideal battery would provide a constant potential difference between its terminals for any current you draw. So with an ideal battery, you could draw 1 milliamp, 1 amp, 1 kiloamp, and you always have the same potential difference across the terminals of the battery. A real battery you buy in Walmart, AA battery, AAA battery, the voltage across, the potential difference across the terminals actually depends on the current you draw. The greater the current that you draw, then the smaller the potential difference. So if we drew 1 milliamp and then drew 1 amp, we'd draw less, we'd have a lower potential across the terminals of the battery. If we try to draw a kiloamp from our Walmart battery, we'd have a much, much lower potential difference across the terminals. And one way we can model that effect is by thinking of the battery as having two components in it. So over here on the left-hand side is what we call the electromotive force. Now, electromotive force is a bad name for what is a electrical potential difference, because it's not a force. I don't know why that happened. It is actually a potential difference. It's a energy. So here's a potential difference, and then also inside the battery is an internal resistance. We normally give it the symbol little r. The consequence of this is that if you draw a small current from the battery, very little potential, very little EMF is dropped across the internal or lost across the internal resistance. And you see almost the full electromotive force between the terminals of the battery. But if you draw a large current from the battery, a much larger fraction of the electromotive force is lost or dropped across the internal resistance. And you see a much smaller potential across the terminals of the battery. And so the picture on the right is kind of the model of a real battery, where as you increase the current that you draw, you actually get a smaller potential across the terminals of the battery. There's a question in chat. I thought greater current was proportional to greater potential. That's Ohm's law. Yeah, great. You know, Ohm's law says that you get a larger current if you apply a larger potential. So this is, on the other hand, a model of how a battery works. And the model of how a battery works is that there's an internal resistance. And the potential that you see is the battery's EMF less what you lost across that internal resistance. So if you're drawing more current, you lose more potential in the battery. If you're drawing less current, you lose less potential in the battery. So Ohm's law is applying to that internal resistance in the battery. Your statement that the current's proportional to the voltage is true for that internal resistance in the battery. But what you get out, if you try and draw a lot of current, is a smaller potential across the battery terminals. Try and draw a little current, it's a greater potential across the battery terminals. Maybe what will help answer that, let me go on to the next slide, because it's an important point, is an equation. So over here on the bottom left, I've turned that model of the battery into an equation. And over here on the right is a related equation. So this equation on the left and this equation on the right are based on this model of the battery containing both a source of electromotive force that pushes the current around the circuit and an internal resistance. So this says that the terminal voltage over here on the left says terminal voltage delta V is equal to the battery's EMF less the potential that's dropped across the internal resistance as determined by Ohm's law. So this is Ohm's law, IR. I little r is a electrical potential. It's electrical potential across the internal resistance. And you see as the current increases, if I were to increase, the potential on the battery would drop. So it is consistent with Ohm's law. If I rearrange this equation and I think of the entire circuit, the current that flows in the entire circuit, so the current here, I, that flows through the internal resistor and what we call the load resistor, the one that we placed in the circuit, that current is determined by the battery EMF, the resistance of the load resist, but it's also governed by the internal resistance. And so that internal resistance lowers the current that you would expect through the load resistor based on simply the electromotive force that the battery supplies. So those two equations help us with understanding batteries. Okay, I wanted to, give you an example of working with the internal resistance and the electromotive force and the terminal voltages of a battery. So we can just use those equations and use those ideas. So in this particular problem, this is an example of a battery's internal resistance. In this particular problem, I've got a circuit, look over here, it contains a battery, a real life battery that we bought at Walmart, and a load resistor across the terminals of the battery. And we're told a few things. The battery's EMF is 15 volts, so this epsilon is 15 volts. The terminal voltage, interestingly, we're told, is only 11.6 volts. So the voltage between this left terminal, this right terminal, is only 11.6 volts. It's less than the 15 volts. It's 11.6 volts when we're delivering a power that is 20 watts to the load resistor. So that's a bunch of information, and we've got to find the internal resistance and the load resistance. Those are our two tasks. So let's see if we can do that. So I did that on the next slide. And so I just redrew on this slide. This is the slide where I imagine I'm in the exam and I'm solving the problem in the exam. And so I've drawn a picture of the circuit, real battery and load resistor. And I've written in the quantities I know. I know the EMF of the battery. I know the terminal voltage of the battery. And I know the power dissipated by the load resistor. So I know all those things. I don't know yet, we're going to figure this out, the internal resistance of the battery and the load resistance. I'm going to figure those two things out. And I did them in two steps. I did the load resistance first, and I did the internal resistance second. Okay, load resistance. Well, I thought about that resistor, right? And I thought, well, I'm trying to figure out the load resistance. But I do know two things about that resistor. I know that there's a voltage of 11.6 volts across the resistor. So I know the terminal voltage across the resistor is 11.6 volts. And I know, so it's delta V. And I know the power that's dissipated by the resistor. You know, that's the energy that's being transferred from electrical energy into thermal energy in the resistor. And I know that power is 20 watts. So I know those two things. So I started to think about how I'm going to get from knowing the power and knowing the voltage to figuring the resistance. And these equations over here on the left, these are my sort of chain of thought. Power, we met this equation in the last class, dissipated in a resistor or dissipated in a conductor is the current multiplied by the potential difference across the resistor or the conductor. So I equals delta V. So, you know, let's think about this. I know the power, and I know delta V. And I want to figure out the resistance. So I've got to rearrange this a little bit. So the next step I did was I replaced the delta V using Ohm's law with IR. So you could get that equation. That's another equation for the power. Or again, if you replace the current with delta V over R, which is also Ohm's law, you would get this equation. So the equation that we met in the last class for power dissipated, you can make two alternative versions of it over here on the right, replacing either the current or the voltage using Ohm's law. And if you look at the second one, then that equation for the power in terms of the voltage and the resistance, well, we know the power, we know the voltage. The only thing we don't know is the resistance, so we can turn it around. And so I did that here. The resistance of the load resistor is the square of the voltage divided by the power dissipated. It's the 11.6 volts squared divided by 20 watts. And if you do that calculation, you get the 6.73 ohms here. And so that was my solution to what is the load resistor. Now I know the load resistor, I can start thinking about the internal resistance and figuring out what the internal resistance is. And so that's what I did down here in this second part of the problem. We've done this part of the problem. Now we're going to the second part. Okay, so I started to think about the circuit as a whole, and I started to think, well, you know, let's figure out the current that's flowing in the circuit, because that current goes through the internal resistor and the load resistor. So I applied again Ohm's law to the load resistor, but now I know the resistance and I know the potential difference. I can solve it for the current. And so I figured that the current that's flowing around this circuit is 1.7 amps. And what I'm reasoning is that once I know the current that's flowing around the circuit, that will allow me to figure out the load, the internal resistor here inside the battery. And the way I'm going to do that is using that equation that we met on the prior slide that is based on the model for the battery. The equation that says the terminal voltage is the EMF less the voltage drop across the load resistor, the internal resistor. So that's the IR. And I just rearranged that. And if you look at this equation, right, you can divide through by the current, get this equation here. And at this point, right, we know the EMF, we know the voltage across the terminals of the battery. We just figured out the current. We can plug them all in. And here is the load internal resistance, 1.98 ohms. And so we've been able to basically analyze our circuit. We used Ohm's law in analyzing our circuit. We used the model of the battery in analyzing our circuit. And we've been able to deduce from the EMF, the terminal voltage and the power in the circuit. We've been able to deduce the components that were in circuit, the load resistor and the internal resistor. So that's a big step forward. Okay, so now I want to move on. Now we talked about batteries. I want to move on to two topics that are resistors. How do you treat resistors when they're in series? And secondly, how do you treat resistors when they're in parallel? So we're going to do the series case first. And so on this slide, I've got on the left-hand side of the slide, I've got a circuit diagram. Imagine I made up this circuit. And it's got a battery, and it's got two resistors, R1 and R2, on the left and right. And what we're going to try and figure out is what is the equivalent resistor in this equivalent circuit where we just have one resistor, that for the same voltage across the pair of resistors on the left would draw the same current as the pair of resistors on the left. So we're going to try and solve this problem. Well, what's the equivalent resistor, single equivalent resistor that reproduces the circuit of these two resistors here on the left? Now, I want to be clear about a couple of words here. So again, series, what does series mean? It means the components, here the two resistors are connected end to end. It means that they form a single line around the circuit, or a single path for the current around the circuit. It means that, imagine that you're an electron, or I'm an electron. I'm going to walk around the circuit. You're going to walk around the circuit. Then you have to pass through both resistors to get from one terminal of the battery to the other terminal of the battery. That's what we mean by series. Equivalent resistor. What do I mean by the equivalent resistor? The equivalent resistor is a single resistor. And it's the single resistor I replace the pair of resistors, R1, R2 with. That would, for the same battery, for the same terminal voltage, for the same EMF, would draw the same current as the pair of resistors. It would dissipate the same power as the pair of resistors. So that's what we mean by equivalent. So these terms, series and equivalent, are kind of important here. Okay, so this slide, I've tried to make some remarks about the current and the potential differences for the two resistors in series and the equivalent resistor, and how they relate compared to one another. And how those currents and potentials relate compared to one another is really the key to understanding the relationship between the equivalent circuit and the original circuit. And so let me describe the two key points here. The first point is, if you have series resistors, resistor R1 on the left, resistor R2 on the right, and the equivalent resistor in the equivalent circuit, they all carry the same current. The same current from the battery flows through R1, flows through R2, and would flow through the equivalent resistor. So that all the currents are the same. I'll call them I for the equivalent resistor, and I1 and I2 for the individual resistors. On the other hand, for a series circuit like this, the two individual resistors, R1 and R2, they share the potential that's applied to the equivalent resistor. So R1 gets some fraction of it, R2 gets some other fraction of it. And if you add them up, the potential across R1 and R2, that's the potential across the equivalent resistors. So that's the features, or these are the keys of a series arrangement of a pair of resistors. Let me just show you a little demonstration, if I can here. Okay, so I hope you can see my Canvas page and a little video I've got here. And I'm going to just hook up a series circuit made out of 2 light bulbs and actually the mains outlet. And we'll just look at this series circuit and get to appreciate this series circuit. I want to explain, though, that this demonstration is actually an extremely dangerous demonstration, and I have to be very careful when I do this. And the university safety officer would ban this demonstration if he ever found out about this demonstration. So please don't tell him. So this demonstration, I actually hooked this arrangement of clothes hangers or whatever they are to the power outlet. So there's 120 volts on these connectors here. And I'm carefully hooking up these regular light bulbs to it, and I'm going to flip the switch. And I've made, as I'm demonstrating, a series circuit here, and we just flowed current through that series circuit, and the light bulbs are lit. And the light bulbs are just resistors. They're just resistors that glow according to how much current is passing through them. And you see these 2 light bulbs glowing as the same current is passing through the light bulb on the left and the light bulb on the right. So that's R1 and R2 in my little demonstration here. Okay. Let me go back to my slides, and we're going to analyze that a little bit more. And we're going to find out, actually, on this slide, we're going to derive on this slide the relationship between the equivalent resistor and the individual resistors. And we're going to solve it based on the understanding that the same current goes through the resistors, R1 and R2, but they share the voltage of the equivalent resistor. So I'm going to start in this derivative. I'll go get my pen going again, sorry. I'm going to start with this key fact about the series resistors, that they share, delta V is the voltage across the equivalent resistor. Delta V1 and delta V2 are the voltages across the individual resistors, and they share that total voltage. And then I'm going to plug in Ohm's law. So, V equals IR, or delta V equals IR. I'm going to plug it in for the internal resistor, resistor number 1 and resistor number 2. Then I'm going to use the fact that the other key to the series resistor circuit is that the current through the equivalent resistor and the individual resistors R1 and R2 are all the same. So this I1, this I2 are the same. They can all cancel out. And we get this relationship between the equivalent resistor. The equivalent resistor is simply the sum of the 2 individual resistors. Now that's true if you've got a pair of series resistors. More generally, supposing you had 3, 4, 5 resistors in series. The equivalent resistor is just the sum of those individual resistors. That's what I'm trying to indicate here. Here's the sum, the sigma, of the individual resistors. Ri is like R1, R2, R3, R4, R5. So that's a simple rule for how series circuits of resistors work. A few comments about it. It means that when you put individual resistors in series, you're making a bigger resistor. You're always making the equivalent resistor is always bigger than all the individual resistors. So that's a key point. Okay, so let's solve a circuit problem involving the individual resistors and the equivalent resistor. Let's take a look at this problem here. So in this circuit problem, I've got a 6-volt battery. I'm going to imagine it's an ideal battery. And we've got two resistors, R1 and R2. They're 2 ohms and they're 4 ohms. So that's the arrangement that we've got. And we've arranged those resistors in series. And what I'm going to try and figure out is the currents flowing through the individual resistors, the potentials across those individual resistors, and the power dissipated in the individual resistors. I'm going to figure those 3 things out. So the first thing I did was think about, because this typically helps in these circuit problems, it's almost always helpful in these circuit problems, is to think about the equivalent circuit. I just can't go one class without doing that. Okay, equivalent circuit. Over here on the left-hand side, I've sketched out the original circuit. So this is the one that contains the pair of resistors, R1 and R2, in a series circuit with the battery. And then over here on the right, I've drawn the equivalent circuit where I've replaced the pair of resistors by an equivalent resistor. And that equivalent resistor, we've learned, is simply the sum of the resistances of the individual resistors. So it's 6 ohms. So that's the equivalent circuit. And using the equivalent circuit, using Ohm's law, we can solve the problem of what's the currents flowing through the individual resistors, voltages across the individual resistors, power dissipated by the individual resistors. I'm going to do all those things on the next slide. All we did on this slide really was understand that we can, if useful, think of the original circuit as an equivalent circuit. And if we do that, the equivalent resistor is 6 ohms. It's just the sum of the 2 and the 4 ohms. Okay. Well, upstairs, I just redrew the original circuit and the equivalent circuit. So nothing new there. But this slide contains my calculation of the currents through R1 and R2, the potentials across R1 and R2, the power dissipated in R1 and R2. Let's start with the current, right? The current is the easy one here to start with, because the same current flows through the equivalent resistor as flows through resistor R1 and flows through resistor R2 in a series arrangement. So I1 and I2, they're all the same. So that, remember, that was the key of the series circuit. The currents are all the same. And those currents we can write with Ohm's law as the potential difference across the equivalent resistor divided by the resistance of the equivalent resistor. And that's convenient because we know the potential difference, it was 6 volts, and we know the equivalent resistance is 6 ohms. And so that tells us that the current in the equivalent circuit is 1 amp, and also in the original circuit with the 2 resistors is 1 amp. And the current through resistor number 1 must be 1 amp, and the current through resistor number 2 must be 1 amp. So that's actually great. We've solved that pretty easily. So now let's think about the potentials across the individual resistors. That's what I'm going to think about in the second part of the problem. Well, look, think about R1. Let's focus on R1 first of all. We know its resistance is 2 ohms. We know the current flowing through it is 1 amp. Well, Ohm's law connects that resistance of 2 ohms, that current of 1 amp, to the potential difference across its terminals. And so we can just apply Ohm's law for the first resistance. The voltage difference equals the current times the resistance, and feed in 1 amp of current through R1, 2 ohms of resistance for R1. That's 2 volts of potential across R1. We can do the same thing, exactly the same thing for the second resistor. Second resistor, Ohm's law applies also, that the potential across it is the product of its current and its resistance. We know its current is 1 amp again. We know its resistance is twice as big, 4 ohms, so there must be 4 volts across the second resistor. And so we've solved the second question, the voltages across the potential differences across the individual resistors with Ohm's law. Look, we've got 2 volts across the lower resistance resistor, 4 volts across the higher resistance resistor. The total is 6 volts, which is what the battery is providing. So that makes sense. Third question was figure out the power dissipated in the resistors. Well, look, we met some equations for the power. One in the last class is the voltage across the resistor times the current through the resistor. We met 2 new versions in this class where we replaced the current in terms of resistance or replace the voltage in terms of resistance. This problem, we just need that the power is equal to the voltage times the current, the voltage difference times the current. So for the first resistor, I labeled its power P1. Then the voltage times the current is going to give us the power. Delta V1 times I1 is going to give us the power. The voltage is 2 volts. We just found that out in the second part of the problem. The current is 1 amp. We found that out in the first part of the problem. So it's dissipating 2 watts, 2 joules per second. Same idea for the second resistor. So the power dissipated in the second resistor is, again, just the voltage across the terminals of the second resistor times the current that's flowing through the second resistor. So delta V2 times I2. Voltage across second resistor is 4 volts. Current through second resistor is 1 amp. Multiplying those together, we get 2 watts, 4 watts. And so that's the power dissipated in the second resistor. And that's the answers to the last part of the problem. So we solved a laundry list of questions about resistor R1, resistor R2, the currents, the potentials, the powers, based on how did we do it? We did it with the concept of the equivalent circuit and the resistance of the equivalent circuit, and with repeated use of Ohm's law. We found that both resistors carry 1 amp of current. The 2 ohm resistor has 2 volts across it. The 4 ohm resistor has 4 volts across it. The 2 ohm resistor dissipates 2 watts and the 4 ohm resistor dissipates 4 watts. Let's move on. Let's move on to parallel resistors. Oh, before I move on though, I was really proud of finding this this photograph. It's a kind of gravitational analogy or a water analogy to the electrical circuit and to electrical current. So in series resistors, right, the same current flows through each resistor. And the gravitational potential, the electrical potential is shared between the series resistors. in this waterfall here, the same water current is shared by each of the steps. So that water current flows across each of the steps. But the gravitational potential difference, that's shared by the steps. The first step gets a little bit of it, the next step gets a little bit of it, the third step gets a portion of it, and so on and so forth. The equivalent waterfall, like the equivalent resistor in an electrical circuit, the equivalent waterfall will carry the same water current as this waterfall through the same potential difference as this waterfall. And so there's a nice water analogy, a nice waterfall analogy of the series resistor circuit, of the electrical potential in the series resistor circuit. Okay, let's talk about parallel resistors now. So this is a sketch of the parallel arrangement that we're going to be thinking about. Over here on the left-hand side, I've got a battery and two resistors, R1 and R2 again, and now I've arranged them in parallel. So I've got resistor R1. If you look, it's connected across the terminals of the battery. And resistor R2 is also connected across the terminals of the battery. So this is a parallel arrangement. So that's the circuit on the left. And here's the equivalent circuit, where I replace the individual resistors with a single equivalent resistor. So that's the equivalent circuit. Now I want to make sure again that we're clear about what I mean by parallel. Parallel means that both these components, R1, R2, are connected across the battery terminals. That makes them in parallel. It means that the current has multiple paths to get around the circuit. In this case, the current has two paths to get around the circuit, either through resistor R1 or through resistor R2. It means that, imagine you're an electron for a moment, or imagine I'm an electron. If I was to walk around the circuit, you were to walk around the circuit, you'd either have to walk around through resistor R1 or walk around the circuit through resistor R2 to get from one terminal to the other terminal. You don't walk through both the resistors. That's what we mean by parallel. Equivalent. What do we mean by equivalent again? So the equivalent circuit is the circuit containing a single resistor that draws the same current as the pair of parallel resistors R1, R2. It dissipates the same power as the pair of parallel resistors R1 and R2 if the same voltage is applied to the equivalent resistor as is applied to the circuit with R1 and R2 in parallel. So that's what we mean by equivalent. And again, it's a powerful idea concept for understanding these circuit problems. Okay, so in the series circuit, we then, after drawing the series circuit and the equivalent circuit, we went on to make two key statements about the series circuit. In the parallel circuit, after drawing the parallel circuit and the equivalent circuit, I want to make two corresponding key statements about the circuit. And they're downstairs here. So the first one is that in the case of a parallel circuit, parallel resistors, the parallel resistors, R1, R2, they have the same potential difference across them as the equivalent resistor, R equivalent. So that's a key point. That the potential across R1, the potential across R2, and the potential across the equivalent resistor are all the same because they're all attached to the positive and negative terminals of the battery. Second point, second key point, the parallel resistors actually share the current that's flowing through the equivalent resistor. So current I flows through the equivalent resistor. I1 and I2 flow through the individual resistors. R1 gets some fraction of the total current. We called it I1. R2 gets some fraction of the total current. We call it I2. And so they share the current. So that's the other key idea. The two resistors share current and get the full potential differences. That's actually the complete reverse of the series case, where in the series case, the resistors share the electrical potentials, but get the full current. I want to show a demonstration of this circuit. So let me share a different screen, if I can. And so I hope you can see back in the, it brings up those memories of bringing, every time I see this, being in that wonderful chemistry, physics, large lecture room. So here I am, and I'm going to rearrange this circuit and make the parallel circuit. I'm thinking about it, at least. I switched it off, which was really a good move. Okay, so now I've got a plan. I'm going to arrange these two light bulbs, or these two resistors, in parallel now. This is where it's really important that you switch it off before you put the light bulbs on. I know that from personal experience. And I've got just a piece of wire here that I'm going to complete the circuit with. And I'm going to point out to you the two paths around the circuit, the sort of top path where I went through the upper light bulb, and the lower path where I went through the lower light bulb. And now I'm going to throw the switch. And here we see the currents flowing through the two resistors that light the light bulbs that are the two resistors. And they're sharing the total current that's flowing around the circuit. They're getting the full voltage, the full potential difference that's applied to the circuit. And so that's what's going on in that overhead. Okay, let me go back to my slides. And I want to make the same step next as we did with the series circuit, where I want to figure out the relationship between the equivalent resistor and the parallel and the individual resistors. So there's a couple of questions in chat. Let me see. Is the brightness of the bulbs due to the current passing or the potential difference? Actually, that's a really great question. You know, the more current, the brighter the bulb. But the brightness of the bulb is actually a reflection of the power dissipated or the energy supplied to the light bulbs. And so you might have spotted that in the parallel arrangement, the light bulbs were much, much brighter. And they're much, much brighter because, well, the current is twice as big, because instead of sharing the outlet voltage, they get the full outlet voltage. So they get twice the current, but the bulbs seem more than twice as bright, I think. The bulbs are actually 4 times as bright because the current doubled. But if you think about the equation for the power, one way of thinking about it is I squared R. So if you double the current, you quadruple the power for a given light bulb, for a given resistor. So those light bulbs are actually burning 4 times brighter because there was 4 times more power dissipated. So the light bulbs actually show you the power, not the current, not the potential difference. That's a great question. Mohammed thinks he wants to go to medical school. right now. But actually, he must be actually a physicist. And so that was a fantastic question. Okay, so what's the relationship between the equivalent resistor and the individual resistors? So let's see if we can figure that out. And we can figure that out using those key statements that we said about the relationship between the currents through the parallel resistors and the equivalent resistor, and the relationship between the voltages across the parallel resistors and the equivalent resistor. And so that's what I'm going to do here. I'm going to figure the relationship between the equivalent resistance and the individual resistances. So my starting point is going to be this key idea. This was the idea that the individual resistors in the parallel circuit share the total current. One of them gets a fraction of it, the other one gets the remaining fraction of it. So I equals I1 plus I2. We can feed in Ohm's law to that equation or that concept. So I can replace I with the voltage across the equivalent resistor divided by its resistance. And likewise, I2 and I2, I'll replace them with their voltages divided by their resistances. And then I can note the other key point that the voltage across the equivalent resistor, delta V, and the voltages across the individual resistors, delta V1, delta V2, they're the same. And so those can be canceled out. And that leaves me with this. This is the relationship between the equivalent resistance and the individual resistances. In a parallel circuit, the inverse of the equivalent resistor is the sum of the inverses of the individual resistors. And that's the rule. And that applies not just to a pair of resistors. Over here, I wrote the general equation. The inverse of the equivalent resistor, if you have 3, 4, 5, 6 resistors in parallel with one another, is just the sum, that's the sigma here, the sum of 1 over the individual resistances. So 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4. Sounds like a sum. Okay, so that's an important point. And as a key point about when you make equivalent circuits is that the resistance of the equivalent resistor is always going to be smaller than any of the individual resistors that made up the circuit. So with series resistors, you're always making a bigger equivalent resistance. With parallel resistors, you're always making a smaller equivalent resistance. Okay, I want to just work through a quick example of this concept of an equivalent circuit, and again, Ohm's law, and using Ohm's law. And so in this example, we're going to think about the equivalent circuit for a pair of parallel resistors, and we're going to figure out, using that concept, the potentials across the parallel resistors, the currents flowing through the parallel resistors, and the power dissipated in the parallel resistors. And our particular circuit was one where I simply arranged that 2 ohm resistor, that 4 ohm resistor, and the 6 volt battery in parallel with one another. It's this guy here. Okay, so the first thing I did, as I would always do, is make a sketch. So here's my diagram of the original circuit. The components, the 2 ohm, the 4 ohm, the R1, the R2 are in parallel with one another. And here's my diagram of the equivalent circuit containing a single resistor that draws the same current, dissipates the same power for the same applied voltage. So this is the equivalent circuit. And I added to that a little calculation, right? So what's the value of the equivalent resistance? Well, the inverse of it, the inverse of the equivalent resistance, is going to be the sum of the inverses of the individual resistances. So we got a 2 ohm resistor, its inverse is a half. We got a 4 ohm resistor, its inverse is a quarter. So a half plus a quarter, challenging my elementary school education now. A half and a quarter is 3/4. And the inverse of, so that's the inverse of the equivalent resistor. So the equivalent resistor itself is 4/3 ohms, the inverse of 3/4. And so that's what I wrote down here. So I got to thank at this point Mrs. Perkins, my elementary school teacher, for that quick memory of fractions. Okay, so now we know the original circuit and we can picture the equivalent circuit. I just reproduced them on this slide. The upper part of this slide is nothing new. It's the old slide. We can go on and do the calculations. We want the potentials across the individual resistors, we want the currents through the individual resistors, and we want the power dissipated by the individual resistors. So let's go through these one by one. It'll be quick. The potential, well, you know, that was the whole point about parallel resistors. When you arrange them in parallel, the potential applied to the circuit or the equivalent resistor is the same as the potential applied to the individual resistors. So we got 6 volts. The potential from the battery is across the terminals of all of the resistors, the equivalent resistors or the individual resistors, so that all the potentials are 6 volts. What about the currents through the individual resistors? Well, now we know that they all have 6 volts across them, and we know their resistances, then we can find their currents using Ohm's law, using delta V, potential difference, equals IR, current times resistance. So applying that to resistor number 1, if we apply to resistor number 1, the current through resistor number 1 is the potential across it, 6 volts, divided by its resistance, which is 2 ohms. Dividing 6 by 2, again, thanks, Mrs. Perkins, that's 3 amps. Same thing for the second resistor. The current through the second resistor, I2, according to Ohm's law, is the potential across the second resistor, delta V2, divided by its resistance. The potential is 6 volts again. The resistance is 4 ohms again, 6 over 4. Thanks again to Mrs. Perkins. That's 1.5 amps. And so those are the 2 currents. The resistor with the smaller resistance has a bigger current. The resistor with the bigger resistance has a smaller current, given that they have the same voltage across them. Finally, we want the powers. Well, now we know the voltages across the resistors and the currents through the resistors. Power is a simple thing to calculate. The power in resistor 1 is simply the product of its voltage and its current. That's one way of calculating it. We could also use I squared R or V squared over R, but let's just use delta V times delta times I. 6 volts times 3 amps, that's 18 watts. Second resistor, what's the power through it? Well, the power through it is its voltage, terminal voltage, times its current. That's 6 volts again, times this time only 1.5 amps. So that's 9 watts. And so that's the answer to that problem. So that's a great achievement, and we've been able to do that. Okay, what next? I think I've got a nice calming picture to show you. Yeah. Okay, so here's a beautiful bit of scenery. You've got this nice little river wandering through the countryside, and it's an analogy of resistors in parallel. That's why I'm showing it. I'm not like, it's not a moment of mindfulness in this sort of maelstrom of physics equations. Here's one path that the water can travel down the river. and here's the other path to the left or right of the little island that would be nice to visit. And this is analogous to, this is a gravitational analogy or a water analogy of electrical potential energy or electrical currents. So in our parallel circuits, right, the current could flow one of two paths to navigate down the same electrical potential difference. And here the water can flow one of two paths to navigate down the same gravitational potential energy. And so this is analogous to the electrical case of two resistors in parallel. The same total water flows through the two paths. If you add up the flow of water through the path on the left and path on the right, that's the total flow of water down the river. It's the total flow of water through an equivalent river with just one single path. And so that's a kind of a water analogy, a river analogy of two resistors in parallel. Okay, so I'm going to move on to over the end of this class and in next class, we're going to be looking at more complicated circuits. And so we're going to just start that. This is going to be like putting our toe in the water of more complicated circuits. And I think I'm going to start you off with a quiz question, if my memory's right. Yeah, we're going to start off with a quiz question. And so let me publish that if I'm capable. And in this quiz question, so I'm not being completely unfair to you. I have, you know, I do sometimes get comments that like, you know, this or that question was not fair. So I'm not going to just drop you into a circuit for a quiz question with, you know, both parallel and series components. I'm going to ask you to compare a parallel circuit, simply pure parallel circuit, and a simply pure series circuit. So this is why this is sticking our toe into more complicated circuits. So I need to stop talking though and actually publish this, and that's causing me a bit of a problem right now. Okay, let me go ahead and answer this question. So there's two circuits. There's the parallel one on the left, I called it A in the question, and the series one on the right, called it B in the question. They both have the same 1.5 volt batteries connected to either the parallel or the series resistors, or the parallel or series light bulbs. And the question is, do the light bulbs or the resistors on the left-hand circuit dissipate more power, or the ones on the right dissipate more power? Well, you know, the answer, one way of answering this is just look at the picture, right? The one, if you look at the light bulbs on the left, the parallel circuit, they're bright. If you look at the ones on the right, the series ones, they're very dull. You can barely see them lit. So straight up from the picture, you know that the resistors on the right, the bulbs on the left are dissipating more power because they're producing more light, and the ones on the right, less power, they're producing less light. If you wanted to understand it electrically, of course, we've been describing that. The bulbs on the left have the full 1.45 volts across them, and so they'll draw more current than the bulbs on the left that have half of the 1.5 volts across them individually. So the ones on the left are sharing the battery's EMF. The ones on the right get the full battery EMF. And so the currents are bigger on the left, they're smaller on the right, which makes the powers much bigger on the left and much smaller on the right. So that's the answer to that question. There was a question in chat about will we have circuits with both resistors and capacitors? I'm trying to remember. I think we will later on. That comes up. One thing I've ignored is what happens when you switch on and off these circuits. And we'll talk about capacitors and resistors together when we come to switching on and off these circuits. So we'll have to wait for that a bit. Is it merely coincident that the equivalent resistor, the two parallel resistors, is smaller and the equivalent capacitance for the two parallel capacitors is larger? I don't think it's coincidental. You know, the way you analyze the parallel capacitors and the parallel resistors, the rules are different. And those rules, when applied, gives the end results. I don't have a deeper understanding of that. That's sort of an interesting question. Maybe let me just think about that as I'm sleeping tonight or whatever, and I might have an explanation for it. But right now, I don't. I don't have something deep and meaningful to tell you on that. I want to end with just a couple of slides quickly, if I can. So what we're going to go on and do in the next class is look at more complicated circuits. And here's a more complicated circuit. If you look at this circuit, right, it's got a battery, it's got a bunch of resistors. And overall, it's not a simple parallel circuit, nor a simple series circuit. It's a much more complicated circuit. And so we're going to have to learn how to solve this more complicated circuit using our building blocks of the parallel and series circuits that we've just met. So this is going to be a goal of the next class, but let me give you a hint. So this is me and my therapist. I mean, it's not really me and my therapist, but let's imagine it's me and my therapist. And I'm talking to my therapist about the problems I have with circuits. And this is the advice I'm getting. So, you know, in general, the point is circuits aren't almost any circuit, right? You know, your iPhone circuit or your MacBook circuit or whatever circuit. They're not just simple series parallel circuits. They've got inside them, though, series and parallel parts or pieces. And so it's important to recognize that inside complicated circuits, like inside complicated people, there are simple parts, simple components. And so the way to solve circuit problems is to actually identify the simply series, simply parallel pieces inside the circuit and replace them with equivalent resistors and continue to replace them with equivalent resistors until you get a single equivalent circuit for that circuit that has just one single equivalent resistor. Once you've done that, once you've understood the circuit, like understanding the person, in that way, you can solve the problems of the circuit or the person by, in the circuit case, applying Ohm's law. You just once you know the equivalent circuit, you can use Ohm's law and figure out piece by piece, bit by bit, by applying Ohm's law in different ways to solve voltages, solve currents, and so on, and solve powers ultimately. You can find all the currents, powers, potential powers dissipated in the circuit components. So this is an advertisement for the next class, and we're going to continue this work in the next class. So just to summarize today, we talked about batteries, real batteries, and ideal batteries. And then we talked about parallel arrangements of resistors. We talked about series arrangements of resistors, how to solve those circuits, and the plan for the next class.